The work summarized in the present video abstract was performed at the Donostia International Physics Center, or DIPC, in San Sebastian, Spain. The DIPC Center was created in 2000 by Professor Pedro Echenique with, among other aims, to serve as an international platform for basic science in the Basque Country in the field of material science. Professor Pedro Echenique is a condensed matter theorist serving as current director of the DIPC. He is an expert on the interactions of charged particles with matter, and he is one of the 4 co-authors of the paper. The other 3 co-authors are also condensed matter theorists: Professor Armand Lucas from Namur, Belgium, Marian Sunjic from Zagreb, Croatia, and Giorgio Benedek from Milano, Italy. Over the last few years, while visiting the DIPC, these scientists have worked on a variety of research projects, including the present one. They are seen here relaxing at La Concha in San Sebastián after a hard day's work at the center. They are grateful to Professor Pedro Echenique for creating and maintaining the highly stimulating intellectual environment of the DIPC and for inviting them to join its program of visitors. Armand Lucas will now present a summary of the work.
I would like to present this video abstract by using a title which is slightly different from the one used in the printed paper. I will use a more evocative title, Plasmon Tsunami on C60 caused by electron transfer to a swift, highly charged ion. A highly charged argon ion, argon Q+, where Q may be up to 18, travels through a vapor of C60 fullerenes and passes by one particular molecule. Electrons on the molecule, colored in green in this picture, are strongly attracted by the passing ion. One or more electrons are grabbed by the ion and eventually will drop into a deep Rydberg state. The ion is accelerated by gaining the potential energy lost by the transferred electrons. The transfer causes a plasmon tsunami on the molecule when its remaining electrons rush to screen the hole, represented by a white circle. The plasmon excitation energy is subtracted from the ion kinetic energy gain. The Q+ ion is partially neutralized to Q - S+, where S may be 1 or more. A spectrometer selects the Q - 1+ or Q - 2+ ions for energy analysis and produces energy gain spectra for the 2 kinds of ions. The spectrum of the Q - 1+ ions begin with sharp peaks and ends with a long oscillatory tail. The spectrum of the Q - 2+ ions has a bell shape and many oscillations on top. The period of oscillations in both spectra is 6 electron volts, which coincide with the quantum of pi plasmons in C60. The present paper develops a quantum theory which quantitatively explains the spectra reported by Selberg et al. In Physical Review A53 of 1996. Here is a comparison between theory and experiment for the Q = 15 spectra. It is clear that the theoretical model captures the essential physics of the complex process. The experimental method and the present theory are promising tools to explore inelastic charge transfer processes in distant collisions between highly charged ions and a variety of other molecular or solid targets.